Suppose that we were able to take several different gases, each made of a single element, and we place them in a glass tube. And for right now, we're going to call these tubes discharge tubes. And what we'll do is we'll run electric currents through that gas. And so right here, these are our pictures of our discharge tubes. You can't see it super well on here, but this is sort of the metal part that goes in here. There's a glass piece that goes in that part right there. And then in the middle of this, there is a gas. And so it's a gas made of a single element. So for that gas, we're then going to take it and we're going to run an electric current through that tube. And so the electric current will sort of flow up and through the gas right there. And what happens when you do that is the gas glows. You get a nice, pretty colored glow, and that the color the glow has depends on what gas it is. So different gases have different colors. The gas that we can sort of see over here on the right, I believe, is xenon gas. I think the one that's over here on the far left, hard to tell from the picture, but looks to me, based on the color on my screen, to be hydrogen gas. And then these other two are different elements. And so we get this nice glow. It's very similar to what you get from a neon light. In fact, that's why they call them neon lights, because there's neon that's in a glass tube, electricity is run through, and it causes that gas to glow. So a nice little sort of interesting thing that happens, but it turns out that this is really critically important in understanding how atoms are put together, and specifically about the electronic structure of the atom. So let's take a look and try to see why this is important in chemistry and what this tells us about the atom. So let's take a step back. So if you take white light and place it through a prism and pass it through a prism, and so in this case here is that we have some white light that comes in right here. I'll use a green marker so we can see a little better. So white light that comes in to this glass prism right here. So it's basically a triangular prism that you can sort of see right there, is that the light passes through the prism, and the prism breaks up the white light into its component colors. And so this is one of the things that you may have learned in elementary school, that if you put white light through a prism, you end up with this nice little rainbow of colors that comes out. And from a scientific standpoint, this rainbow of colors that goes all the different colors from red to orange to yellow to green to blue to violet going across there is called a continuous spectrum. It's a spectrum because it covers all the different colors. It's continuous because it doesn't skip any colors. They go from one all the way to the other without skipping any colors in between. So this is what happens when you pass white light through a prism. So here's our question. What if we took one of those discharge tubes, like we saw in the last picture, and put it through a prism? Because we know white light breaks up into the full spectrum of colors. But what if we took some of that colored light that we got from the discharge tubes and put those through the prism? We get something that looks a little bit like this. So in this particular spectrum, what we have is we have our red is over here. I'll grab my red marker. So this is the red side of things. This is where the red is. And then going all the way over, and then on this side is where the blues and the purple colors are here. And you notice that what we have here is, instead of a full spectrum, and you can sort of barely see the full spectrum along the bottom where some light not from the tube sort of managed to sneak in there. But you can see we really only got, looks like 4 different colors. There's sort of a reddish color that's right here. We've got sort of a blue that's right in there. We have 2 purples. There's a purple here and a purple right there. We didn't get the full spectrum. It's not continuous anymore. It's broken up. And so these certain colors and no colors in between. And this happens for all of those different types of gas discharge tubes. So it doesn't matter what element it is. But if you put any element into a tube where it's only the gas of that element, run electricity through it, it'll glow. And when you split those colors up through a prism, it only produces certain individual frequencies, certain individual colors of light. And so this tells us that the light from the emission tube is made up of only a few frequencies of light, not all frequencies like white light that we normally experience. So this is interesting because each element, when you put it through a gas discharge tube, produces only certain frequencies of light and no other frequencies, nothing in between, unlike just about every other light source that we run across. So let's keep looking at this. So let's suppose we actually looked at which colors were produced by which elements. So right here, Here's hydrogen as our first one right here. So hydrogen really only produces just a few different individual colors. It produces this red that's down here. It'll produce this color right here, which looks to be sort of a greenish color. It'll produce a blue right here. And then you can see it has several different sort of varieties of purple that are right in here. I don't know how many of you can see on your screen. I can't see very many on mine, but you can see it only produces those colors. Now sodium, on the other hand, if you take a sodium gas and then run electricity through it, really only produces two colors. There are two little frequencies of light that are in the yellow range right in there. Helium, on the other hand, produces colors, a red, and produces a yellow, and produces then, some blues of different shades, sort of some greenish blues to some regular blues, then over into sort of a bluish purple over here. But you can see each individual element has its own sort of color fingerprint that it puts out whenever you do this. No element shows all the colors of the spectrum. Every single element only shows certain colors, and different elements show different particular colors. Neon has a bunch of different colors, but they're all sort of in the red-orange area. You don't have any blues or greens or anything like that that's over on the other side. So the term for this type of spectrum, we said that like a full rainbow that you get for white light is called a continuous spectrum. These are called emission spectra right here, because of the fact that you put the electricity through the gas and it emits light and emits these different colors. So we'll call these emission spectra right here. So let's suppose that this time we're not going to put electricity through our gas. We're just going to have a container of our gas. It's going to have a transparent side, so we can just shine white light through our gas. Now, normally if you shine white light through something that's transparent, is that the light just passes through, and then once it passes through, you could put it through a prism and you get your rainbow. You get your continuous spectrum again. But it's a little different when you pass it through individual elements of gases. So down here, we have a picture of what would happen if you were to pass white light through lithium gas. So you notice on our picture down here, we get the full rainbow, the full continuous spectrum, but it's missing pieces. There's like a gap that's right in there. There's a gap that's in here. There's a gap there. There's a gap here. There's a gap here. There's a gap here. We can see all those gaps that are showing up there. So there are missing frequencies. There are missing colors when you shine through lithium. Now, because of the fact that these individual colors are being absorbed by the gas, that's the way we have to figure this here, because if the colors aren't making it through the gas, they were there to start with, they're not making it through, the gas had to absorb them, we're going to call these absorption spectra. So an emission spectrum is one where you end up with only a few different colors that come through, and most of the colors do not, because of the fact it's only emitting certain colors, certain frequencies of light. For an absorption spectra, spectrum is singular, spectra is plural. It's only absorbing certain colors of light. And so each element has its own unique absorption spectrum, very similar to the emission spectra, is it where each element has its own. So what if we compare them? What does it look like whenever you compare the emission spectra of an element, the emission spectrum of an element, with the absorption spectrum of an element? And then we say on top we have our absorption spectrum of lithium, and on bottom we have our emission spectrum of lithium. And so you can see that the colors that are absorbed on the absorption spectrum are the same colors that are emitted on the emission spectrum. They line up perfectly. This tells us that there is something about lithium atoms that's important about these particular colors, these particular frequencies of light. And the same thing would be true for all other elements, is that the particular bands of color, or the particular ones that have been taken out of the absorption spectrum, or the ones that are emitted for the emission spectrum, must be important in terms of trying to understand the atom here. So they all show the same frequencies. So let's try to come up with some explanations for this. Each frequency of light, we know from our last lesson, has a definite energy. And so we use this equation is that E equals hf. The energy of electromagnetic radiation equals h, which is Planck's constant. Remember, that was that really, really small number that was 6.626 times 10 to the negative 34th joule seconds. So just that number here times f the frequency. So each individual frequency has a definite energy. So the few frequencies of light that are emitted or absorbed by each element must mean that each atom only emits or absorbs certain energies. So take that hydrogen spectrum that we saw before. it really only had about 4 bands, and I'm just sort of randomly drawing this. I'm not trying to represent hydrogen specifically. And so it's only got 4 different frequencies that it absorbs or emits. And since its frequency is an energy, that means that that hydrogen atom has only certain energies that it absorbs or it emits. And so this is interesting. And so the question is why? So in 1913, Danish scientist Niels Bohr came up with an explanation for this. He came up with what's called the Bohr model of the atom. And so Bohr's idea was that you had a nucleus in the center of the atom and you had electrons that orbited around that atom. And that those electrons were in different orbits of different energies. And he said this, that electrons in each atom could only possess certain energies and no energies in between. So you can think of this a little bit like the difference between a ramp and a staircase. Okay? It's not a very good staircase, but you get the idea. So with a ramp, you can stand at any height on the ramp. So, I can stand at this height or this height or this height or some height in between that or even halfway between that or halfway in between that. And you can basically pick any height you want to. But on a staircase, there are only certain heights you can stand at. If each step is a foot tall, you can stand at the 0 mark or at the 1 foot or at the 2 foot or at the 3 foot. But you can't stand at the half a foot mark because of the fact that there's no half a foot mark because it goes straight from 0 to 1 and straight from 1 to 2 and straight from 2 to 3. There's no way to stand on the 1.5 step. And so Bohr argued that the energies of the electrons in the atom work the same way as a staircase. They are like a staircase, not like a ramp. Is that the energies of the electrons could be at a certain level, or at a different level, or at a different level, but they could not be at any energy in between. And so if this might have an energy of, let's say, negative 6 electron volts, this one might be at negative 3 electron volts, this one might be at negative 1 electron volts for our energy. The electron could be at negative 1 or negative 3 or negative 6, but it could never be at negative 5. And it could never be at negative 3.001. It could only be exactly right at negative 3. This is the argument that Bohr made. And so he said that, each possible energy the electrons could have in the atom, we're going to call those an energy level. And so we'd say that it's negative 1 that we had right here is an energy level, negative 3 is an energy level, and negative 6 electron volts would be an energy level here. And so this is Bohr's argument. So he says, okay, electrons can only have certain energies, and so I can use this to explain why they only produce certain frequencies. They can't ever be an energy that's anywhere in between. So in Bohr's model, energy levels are numbered. And so the lowest possible energy level, we'd say, is 1, or the first energy level. The second lowest energy level is 2, and so on and so forth. So in this illustration we have at the bottom here, the nucleus of the atom would be sort of right in the middle. And so Bohr argued that these energy levels were actually orbits. The electrons actually orbit around the nucleus at different distances, and the closest energy levels were the closest orbits. He actually was a little bit off on that part. Is that there's some bit of what he said that's somewhat correct and some bit that's not. The correct part that what he got there was that these electrons are in these energy levels. And so the energy level that has the lowest energy we're going to call the first energy level. You can sort of see, you can sort of see how that has an n equals 1 right there. The next one out here, which is this one right here, is represented by the 2. It doesn't actually mean the electrons are actually at those places. This is just a way of representing what the energy levels are. So you can see it goes from the lowest at 1 all the way up to, in this case, it shows up to 5. There are energy levels way beyond that, though. There's no real limit on how high of an energy level you can get. So since there are only certain energy levels you can have, that means there are only certain possible energy changes if the electrons change energy levels. So, if I can only be at the first energy level energy, or the second energy level energy, the third energy level energy, or the fourth energy level energy, if electrons were to jump and change energy levels, they'd only have certain distances they could drop from an energy standpoint. I could go from the second down to the first. That's a possibility, but that's only a certain energy drop. Or I could go from the third energy level down to the second. That's a certain energy drop. Or I could drop from the third down to the first. I could go that one. But I really couldn't do anything that's in between that. Over on this side, right over here, I've got an illustration showing what are the different energies of those energy levels. So one thing that you notice here is the first energy level has a pretty low energy. In this case, this is for a hydrogen atom, negative 13.6 electron volts. Second energy level is about 10 electron volts higher, negative 3.4. The third energy level, though, is only about 2 electron volts above that. And then as you keep going up, the energy levels get closer and closer and closer until you finally get to what's called the ionization energy. That's the energy that it takes to knock the electron completely off the atom. If you take a hydrogen atom and you have an electron that's down in that first energy level, and you were to give it 13.6 electron volts of energy, it would, or more than that, it would actually strip the electron off of the atom. And so now you have one fewer electron and you have an ion because you have a positive charge for your atom right there. So this is just sort of illustrating how that works. And so there are only certain drops these electrons can do. And so it can go from the third energy level down to the second energy level, or from the fourth energy level down to the first. But there's no way for it to go from like the 2.5 down to the 1.5. That's not possible because those electrons can't have a second and a half energy level energy or a first and a half energy level energy. They have to be on a particular energy level. So let's take this atom below. Let's suppose that we have an electron that's going to start off in the second energy level. So it starts off in the second energy level. That would be right here, or on this diagram showing the energies would be right here. And let's suppose that it drops from the second energy level down to the first energy level. So we're going to go from the second energy level down to the first. And so this electron is going to drop in energy as it goes from the second to the first, drop in energy as it goes from the second energy level to the first energy level here. And so we can figure out how much energy it would release by looking at our values here. So in this case right here, it starts off with negative 3.4 electron volts of energy in the second energy level, and it falls to the first energy level, which is negative 13.6 electron volts. And so because of the fact that its energy drops, that energy can't be destroyed, can't be created, that's the rule about energy, but it can be released. And so that would mean the difference in energy between these two is the energy that would be released. So if we do that math, negative 3.4 minus negative 3.6, we get 10.2 electron volts. So that means that this electron would have to give up 10.2 electron volts of energy in the process of falling from the second energy level to the first energy level. If an electron were to drop from the third energy level down to the second energy level, so now let's say the electron starts off, a different electron starts off at the third energy level, and so it starts off in the third energy level up here, and is going to drop down to the down to the second energy level. That's another possibility. It goes from the third to the second right here, so the third to the second. We can also calculate how much energy it would give off. It would emit by taking the difference there. And so in that case, we'd say it's going to go from the third energy level, negative 1.5 electron volts, to the second energy level. We take the difference, so negative 1.5 minus negative 3.4 gives us 1.9 electron volts. So it would emit 1.9 electron volts. What if we had one that went from the third energy level to the first? And so this time the electron's going from the third energy level all the way down to the first energy level down here. And so that would be going from 3 down to 1. To find the energy it emits, we take the difference again. So we'd say for that one, negative 1.5 minus negative 13.6. And so if you do that, you get 12.1 electron volts. So if we have electrons that are only in the first 3 energy levels, there are really only 3 different energies they could possibly emit. If they go from 1 to 2, then they'd emit 10.2 electron volts. If they go from 3 to 2, they'd emit 1.9 electron volts. If they go from 3 to 1, they'd emit 12.1. And they can't emit any other amount if they're only in those first 3 energy levels. That's it. And so because of the fact that those are the only possible energies that can be emitted, that would represent that there are only 3 possible colors that could be emitted, 3 possible frequencies of light for electrons in those 3 energy levels. Now, in reality, there are more energy levels than just 3. You know, it could go from the 4th energy level to the 2nd, or the 5th to the 3rd, or something like that. And so that would add more energies, but it doesn't add an infinite number of energies. It only adds certain energies that could be emitted by the electron whenever they drop energy levels like that. And so that means only certain colors should be able to be produced whenever the electrons jump from one energy level to another. So we can use this to explain the emission and the absorption spectrums. So in an emission spectrum, each color line is produced when an electron drops from a higher energy to a low energy. So it emits light. And so whenever we look at our diagram, is that this green that's right here would correspond to one particular drop from some energy level to some different energy level. Maybe it's from the 3rd energy level to the 2nd, or the 5th to the 4th, or the 5th to the 7th to the 2nd. We don't know right now. We'd have to actually do some calculation to figure that out, which we'll learn how to do later. But we know that each individual color corresponds to an energy drop from one energy level down to another energy level within that atom here. And the fact that only certain colors is because there are only certain drops that can be made. Now, on the other hand, in an absorption spectrum, if we were to look at that one, each missing color occurs because the electrons absorb that exact amount of energy needed to jump up energy levels, but no other amount. And so this is a case where the light's going into the gas, and so we start off with an electron that's at the lower energy level. So let's say we're going to pick just this amount of energy right here. You know, it's not on the absorption spectrum. That was not one of the dark lines that we saw on that absorption spectrum here. And so that energy might be enough to take the electron from here up to this point right here. But there's no energy level there. And since there's no energy level, it's like trying to step up a step. And if a step's a foot high, but you only raise your foot up by 6 inches, you'll never get up the step. You'll just fall back down to the previous step. And so because of that, the electron just goes right back down to the energy level it was on before. And since it's there, there's no change. And so it never emits any light because of the fact that there's no energy loss. The electron started on, say, the second energy level and ended on the second energy level. But if it happens to correspond, if the light that comes in has an energy that's exactly equal to the difference between energy levels, the electron will jump from a lower energy level to a higher energy level. And when it does that, it's absorbing energy because that electron took the energy from the light, it used that energy to jump up energy level, so now it's on a higher one. And since it absorbed that light, that means there's no light that passes through of that color anymore. It's all just going to be the color. So the only colors that pass through for an absorption spectrum are the ones that don't correspond to differences in energy levels, but the places that are missing, those missing dark lines that are on the absorption spectrum, are the energies that are exactly right at the energy levels. And notice, of course, we said those match up because each difference, each line on either the absorption or the emission spectrum matches up exactly with each other because they match up exactly with the difference in energy between energy levels. So that explains why each element has only particular colors in its spectrum, whether it's an absorption spectrum or an emission spectrum. But why do different elements have different sets of colors? Why do they have different sort of light color fingerprints there? Well, the reasoning is this, is that different elements have different numbers of protons and different numbers of electrons. And so the protons pull those electrons in, the electrons push on other electrons, and that affects the energy of the other electrons, and it affects the energy levels. And so as a result, the energy levels of different elements are at different energies. So if you look at, for example, hydrogen, helium, is that first energy level for both of these. The first energy level for hydrogen has an energy of negative 13.6 electron volts, but the first energy level of helium is negative 24.6. That's largely due to the fact that there are more protons in helium than there are in hydrogen, and a little bit due to the extra electron that helium has, that hydrogen doesn't. And so because of the fact that you have different energy levels at different places, is that, say, hydrogen might be here, but helium's energy levels might look a little bit more like this. And so the jumps between them, so a jump from first to second in helium is not the same energy as a jump from first to second energy level for hydrogen. And so as a result, is that these would be two different color lines on their spectrum. So each element is going to have its own unique sets of energy differences between its energy levels, and so will release or absorb a unique set of energies. And if it's a unique set of energies, then it'll be a unique spectrum of frequencies and a unique color spectrum. And we can use these to identify what the elements are. So let's look a little bit at these energy levels in a little more detail. So the first thing we need to know is atoms are most stable when electrons occupy the lowest possible energy levels. And so it's just like things in general, is that, you know, objects always want to, if they're free to move, occupy the lowest possible potential energy they can have. And so if you drop an object, it falls to the floor because it's trying to lower its gravitational potential energy. The same thing is true about these electrons in the atom, is that if I have, I have my nucleus right there, and we're going to use that same sort of illustration. Of course, physically it may not necessarily be like this, but we have, our first energy level, our second energy level, our third energy level. If there were no electrons in this atom, that first electron would go to the lowest possible energy level, which would mean that it would basically go to the first energy level. And if I had another electron, it would go to its lowest possible energy level, which would be the first energy level. Now, you can fill up energy levels, though. Energy levels only hold certain numbers of electrons. First energy level, for example, for all atoms, can only hold a maximum of 2 electrons. So if I had to add a third electron to an atom, it couldn't go in the first energy level, even though that's the lowest possible spot. That one's filled after you already got 2 in it. So the next electron would go to the second energy level because it's the lowest available energy level for it to go into. It has the lowest available energy. So like for example, hydrogen has 1 electron in the first energy level because it fills it up. Carbon, on the other hand, which has a total of 6 electrons if it's a neutral carbon atom, has 2 electrons in the first energy level, filling it up, but the next 4 go into the second energy level because there's 6 total spots that are available for electrons in the second energy level. We'll talk about how to know how many electrons fit in each energy level later. So, as we said, if all the electrons in an atom are, well, we'll say this, if all the electrons in an atom are in the lowest possible energy level, we say that atom is in its ground state. Just like if you drop something and it falls to the floor, if it's at its lowest possible energy, it's on the ground. We also say the same thing about our electrons, is that if the electrons are all filled up at the lowest levels they can, that they haven't skipped any available spots, any lower possible energies, we say that atom is in the ground state. And most atoms that we deal with on an everyday basis are in the ground state, unless they're doing something more interesting, which is next. So to make things interesting, let's suppose that we have an atom that absorbs energy, like for example from light, electromagnetic radiation, or like we talked about the discharge tubes, we run electricity through them. Those atoms will absorb energy. And so that can cause those electrons to jump from the lower ground state energy level up to a higher energy level. So let's say that we have a hydrogen atom. It has its electron in the first energy level because that's the lowest it can be because it's at the ground state. And we zap it with some electricity. That might cause that electron to jump up to, say, the third energy level. And so now the electron is no longer in that first energy level anymore. It's in the third. But if it's only 1 electron in the third, it's not in its lowest possible energy state. And so when this happens, we say the atom is in an excited state. It's no longer on the ground, it's up, it's excited. So anytime you have any electron, it could be just 1. You could have an atom that has 120 electrons in it. And if even just 1 electron is not in its lowest possible energy level, where it skips a spot, it's to be the lowest energy in the third energy level, and instead it's in the 5th or something like that, we'd say that atom is in the excited state. Now, over time, what will happen is these electrons in the excited state atoms will fall back to their lower energy levels, and the atom will return to the ground state. So, temporarily, for our example hydrogen atom, the electron's in the third energy level, because it's now an excited state, but it will eventually fall back to the first energy level again. And then when it does that, it'll emit that energy that came out from it. So this would be an example of, like, say, glow-in-the-dark stickers. You shine light on them. When you shine light on them, that causes, they absorb some of that light, which causes the electrons to jump from a lower energy level to a higher energy level, and then they stay there for a while, and then over time they fall back down, which emits that light, and that's why the stickers glow later on. So that's how the glow-in-the-dark sticker basically works here. And now the atoms in there are back to being at the ground state again.